record right now. Represent. There it is. Yeah. Pen's there. I think that's the pen. Okay. So let's present my screen. Okay, hopefully you can see some page table looking stuff right now.
Yes,
cool.
Sir.
Okay, great. So then I wanted to start off today basically by just taking another look at paging. And actually, I'm not going to, let me see if I can view this in a slightly bigger frame, but not quite like this. It's the best we're going to get, actually. So what I wanted to talk, I just want to kind of go through paging a little bit more, make sure we're all on the same page, pardon the pun, moving forward so that we've got a good idea of how paging works, and we're not sort of behind on that. And then we can go back to TLBs and some of the optimizations that we're going to look at for paging so that everyone's sort of ready to understand that material. So what I have set up here is a 16-byte memory. So not much space at all, but 16 bytes just so that I can represent it. We have the process 1 virtual memory on the left here. So there are 16 different addresses because of the fact that it's a 16-bit space. We need 2 to the 4th different options to represent 16 different addresses, which means we need 4 bits, which is the same as 1 hex digit. So, this address is really 4 bits, 0, 0, 0, 0, 0. But I'm just going to represent it as hex 0 instead. So we have 16 addresses. Each of those addresses maps to a single byte of data. So all of the data is there's 2 hex digits, right? So that's 8 bits. And again, we could translate AB to 1010 1011 in binary if we wanted to, but we're just going to represent it as OXAB instead for now. So that's what we're looking at here. And I have it helpfully color-coded to get you started. So we can see here that we have virtual memory for process 1. Some of that virtual memory is mapped to physical memory in DRAM, but not all of it is mapped to physical memory in DRAM. And it doesn't necessarily correspond from like a page in virtual memory being the same page in physical memory, right? So the mapping that we have here is that page 0 is actually mapped to frame 1. We can see that the addresses are going to be slightly different here because we are looking at a different frame number, and the data is going to be the same because we are in fact mapping this entire page, page 0 here, to frame 1. So in our page table, if we were mapping this, we would change it so that we have page 0 mapping to frame 1, and we would say that that is a valid mapping currently. So we're essentially notating that whenever we have anything going to page 0 in virtual memory, we want it to actually go to frame 1 in physical memory. Okay, and we can hopefully see that if we sort of look at the addresses here, if we have the address, OX2 is going to be 000 or 0010 in binary, right? The page number for that address is the first 2 digits of this. Because of the fact that we're using 4-byte pages, so each of these pages is taking 4 bytes, that means we need to have 2 bits for the offset. We have 2 to the 2 is 4, So we can represent 4 different addresses in 2 bits. That means we have 4 byte pages. So our page offset is 2 bits. Our page number is 2 bits here. So the page number we're looking at is 00. And if we're looking at here in the page, we have OX2, the address OX2 is mapping to OX01, the byte data that we have in memory. So that's like the character or some part of an integer we're storing possibly. If we use this mapping, what we do is we take the page number that already exists and we swap it out for the frame number. And that gives us let's maybe do this. So now we have 0110. And that should be equal to, in hex, 0110 is OX6, right? So we've translated from the bit address 0010, which is OX2, to the new bit address in the frame 0110, which is 6, and that gives us the same data in physical memory, right? So by swapping out those first 2 bits, we're able to go from the physical the virtual page to the physical frame that we were hoping to find. Okay. So then we can do the rest of the mappings here. We have that page 01 maps to frame 00 and is valid. And we have that page 11 maps to frame 11 and is valid. Here, because of the fact that right now we can see that like the data 4, 5, 6, 7 is nowhere in physical memory, that means that this page is not currently mapped. This might mean that the process has relinquished this memory, decided that it doesn't need it anymore. It might mean that it's been swapped out to disk, which we'll talk about later today. But basically that means that this is no longer a valid mapping, that this page does not reside anywhere in physical memory. And that's why it's sort of marked off as gray. So we could have any page number in here. Probably the most likely one is that it was at 10. And is no longer at 10 because some other process memory has replaced it. But for right now, we basically rely on the fact that we have this valid bit that the OS keeps track of to say, is this currently a valid mapping from page to frame? If it's not valid, then we're not going to go grab that memory and check on it this way. Okay. Any questions so far? Okay, great. So let's move on to the next slide then. So just again to sort of cover this a second time, let me copy over the page mappings that we're using here. So what the user process would access this as is we would say maybe like store OXFF. So this is the new value that I want to store into memory, and I'm going to store it to address OX3. And OX3 is 0011. So we're going to divide that 0011 again into the page number and page offset. And again, we're using 2 bits here for each of those because we have 4 byte pages, and 2 to the 2 is 4. So that's how many bits we have to use for the page offset. We use the remainder for the page number. And we'll talk about a little bit. I know some people had issues with the 2-level page tables. With doing that reading quiz problem. I am going to extend that to to later today if you haven't gotten that answer yet. So if you want to go back in and fix it up, you're welcome to. I know it was a little difficult for a reading quiz maybe. So here we're just using a single page number. So whatever remaining bits go into that page number. And that means we have 00 as our page number, 11 is our page offset. We're going to translate again. We have 0011. We're going to translate the frame number by looking it up in this page table. So we're going to just look at each page number here. We're going to find the 00 in it, and then we're going to replace it with the frame number 01, and we're going to leave the page offset the same. So the page offset is never going to change when we map from a page to a frame. That's always the same value. We're assuming that the pages and frames are the same size. And so we're not going to change that page offset. We are definitely, though, going to change the frame number in order to map to the correct data. And here we see that again, just like before, we go from address OX3 to address OX7. And what we would do is then we would write both into virtual and physical memory that value FF. And really what's happening here is that there's not an actual write to virtual memory. It's just that virtual memory has been mapped onto physical memory in this way. And so when we write to address 0x7, because of the fact that this page is mapped to that address, we are, virtually writing to page 0 at address 3 at address the value FF. So there's no actual like virtual memory in this system. It's just that we have the virtual memory mapped to the physical memory. And so when physical memory gets written, it updates what we're seeing as virtual memory. Okay. Any questions so far? Hopefully this is clarifying things a little bit here. So let's continue on then. I think this is just the same thing. So let's see if we have another process now. So each process has its own virtual memory, and each process has its own page table. Sorry. Yes.
There is a question.
Okay.
By Ryan. It's on the chat for
okay.
Hangouts.
Yeah, I was
Thank
just asking,
you.
how did you pick out X7 for the frame number?
How did I pick X7 for the frame number? So we're doing the same translation here. So we have 0x3 as our original address, which is 0011. And that gets translated by just substituting the frame number for the page number. So we look up this page number 00 in this table. And then once we find that page number, we are going to substitute the corresponding frame number for the page number. So we're just taking that 00 and changing it to 01. And then that gives us 0111 is equal to 0x7 in hex.
Got it. So that's what the page table does. Got it.
Yeah, so that's what the page table does, is just this sort of substitution of we look up the exact number that we have for the page number in bits, we substitute it for the bits that we have for the frame number.
That
Okay.
makes sense.
Cool. Okay, yeah, I'll try to keep an eye on chat, but thank you, Kira, for letting me know. So now if we have two processes, they each have their own virtual memory. So again, this is sort of the big benefit of virtual memory versus not having virtual memories. Every process gets to think that they have all of the memory in this system. So you can access memory as if you own all of it, as long as you've told the OS that you want to possibly use that memory. So we have two processes now. They each have their full address space, that full 16-byte address space. We have physical RAM, physical memory that has the full 16-byte address space, the full 16 bytes of memory, and some of these are mapped onto physical RAM. So we have the same mapping for process 1 that we had before. We have that, there was something mapped at page 10 at some point, but it's no longer mapped. So we can see now that what's actually mapped there is process 2's page 01. So process 2 is going to use its page table to map addresses. Process 1 is going to use its page table to map page numbers to frame numbers. And we can see here that process 2 has 2 pages that aren't mapped. These are both grayed out, so it's not valid for page 00 or page 10. We can see that this yellow page here, page 01, is mapped to frame 10. And the data should be the same for both of those because, again, this is a physical mapping into memory. And then we can actually see something interesting that we're going to talk about in a minute here, which is that we have page 01 and page 11 mapped to frame 0. So why would we do that?
What was the question again, sir?
So why would we map two pages to the same frame? What does that allow us to do?
I think the answer's in the chat. Yep.
It's
Memory sharing.
disallowing or it's allowing both of them? Yeah, so so page 01 and page 11. So like, let's look at, let's say process 1 does a load from address OX6. And process 2 is going to do a load from address OXE. Okay. Are they going to get the same values? So let's look. So let's do this sort of a frame number and page number substitution for both of these. So let me make this another row. Okay, so we're going to do load OX6 on process 1. So process 1 is going to start with the address OX6, which is going to be 0110 in binary, right? So our page offset is going to be 10. That's the last 2 bits of it. Our page number is going to be 01. Now we take this 01, we look up in process 1's page table, since this is process 1 doing it, and look up 01 in that page table and see that it maps to frame 00. So we're going to substitute that 00 based on that, and that's going to give us the address that we're going to access in real memory, which is going to be OX2, right? Because that's what 0010 translates to binary to hex. So process 1 is going to load from address OX2, right? In physical memory. So process 2 is going to do the same thing now. And I'm going to run out of space here, unfortunately. Let me slide these all down. Can. Sorry. Maybe a little cramped in here. Okay. This is good enough. So process 2 is going to load from OXE. So let's translate OXE to binary. That's going to be, what, 14, right? So 1110. So we're going to look up here. Our offset is still going to be 10, right? Because that's the last 2 bits of that. So we're still going to have offset 10. Now we're going to have page number 11. And because this is coming from process 2, we are going to look this up in process 2's page table. So we have this per process page table that we're always going to use for each process individually. So we're going to look up 11 in this. We're going to see that that maps to frame 00. And so we're going to have 0010. And we should be able to see now that this is the same frame and same page offset as we got for process 1. So this is going to go to OX2, just like page process 1 did. So here, this allows us to share memory. Now we could write to the same page, write to the same frame, and process 1 and process 2 would be able to see those updates, and they'd be able to read those updates because they're mapping their pages to the same frame in physical memory. So the thing that matters is that we have this physical memory that we're mapping these virtual pages to, and whatever happens in physical memory, that's what those processes see when they access that virtual memory. Okay? Questions on that? Let's see some chat things. Okay. Yes, I do have a gaming chair because I sit in this for long periods of time. So, technically speaking, I bought a gaming chair to continue to work on my PhD, but it did have the nice side effect of having a gaming chair for gaming as well. So, yeah. Okay. Yeah, so this is what, that's a good comment, Phil. This is what mmap does, right? So mmap allows us to map pages to the same place in physical and virtual memory, or the same, the same virtual memory to or some virtual memory to the same physical page, the same physical frame. So it allows us to share memory between processes. So when we did this for, checking out how synchronization worked in, between processes, or how inter-process communication worked, this is what they're actually doing, is they are mapping different physical or different virtual pages to the same physical memory, so that both of those processes get to access that physical memory. Okay. So yeah, good comment. Why isn't page number 11 mapped to frame number 11? So they do not have to be the same page and frame. That's part of the point of this, is that we don't have to have a, if process 1 and process 2 are both accessing the address 4, right? So they both have valid mappings for address 4. But we want to make sure that those go to different places in physical memory if those are not shared memory. So we want to make sure that we don't have those. I mean, we could make this a little simpler, right? If we could always map the shared memory to the same place, like if we had the blue page here, the blue page at 01 instead, then we have the same mapping for both processes. But that's not always feasible, because both of these processes might do different things. They might use different amounts of memory before they get to sharing memory. And so it's not always feasible to enforce that the page number maps to the same frame number, which is why we have this set up in the first place, is so that, generally speaking, when we run a program, our stacks are always going to be at the same place, because it's easy for the programming language implementation to say the stack goes at, OX FFFFFFF something, and that's where the stack will always start. And the text segment will always start at OX 04 zeros. And so it's easy for the programming language implementation to basically say these are the predefined places where these things will exist, and they're going to be the same for every process. So then, because of the fact that we have those same numbers for every process, we have to make sure they go to different places in physical memory for each process. And yeah, so that's why they each have their own individual page tables, so that we can say that, on this process, address 4 means actually address 0. On this process, address 4 means actually address 8. Page tables are not generated at compile time. A lot of the addresses that your program uses are generated at compile time, but this allows you to map them at runtime. So we talked about address binding, right? The fact that if we have a library somewhere in memory, and we want to write code that calls to that library, we might have to bind the addresses or do something dynamic to rebind them. This can allow us to bind memory that is shared. Like this page 11 might actually be libc. So this may actually not be memory that these processes are explicitly sharing, but it might be a library that we have mapped into memory. And so each of these processes might actually be accessing this based on whatever they were compiled to access, the addresses that they were compiled to use. And this can allow us to basically say, I'm going to put this at one place in physical memory that everything's going to share. But I don't have to have that predetermined before I compile the code, before I run the code. I can just put it wherever it fits in physical memory, and then I can remap the virtual memory, the page to frame translation for each process to say, okay, every time you access this place in memory, you're actually going to go to here and get that library. So this can allow us to share for a number of different reasons, mainly to share things with mmap, and then to share libraries that we've put into memory. So I can actually show that probably quickly here. If you ever get a chance, please thank my advisor at Penn. Not that you will ever have that opportunity, but he's being nice and letting us or letting me use this server in order to be able to show things during class. So it's cat/proc 16. Doesn't matter. Oops. Be a system process. It's not actually showing me anything. That's weird. Usually when you cat maps, that should show you all of the process memory, but it's not showing it. So sorry, we should be able to see where everything is in memory when you're running a process, but I can send out a screenshot of that so we can see that. You can see what actual Linux system looks like when you're what's in memory. Okay, so now let's talk about the TLB in context of this. So we had this original setup here that we have one process. It maps to physical memory somehow, and then we have this thing called the TLB, which is a cache. And this cache is from pages to frames, and it basically keeps this at hardware. So we have the ASID, that is the address space identifier. We have the page number, and we have the frame number. So the important thing is that this is kept in hardware. So this is a quick translation from page number to frame number. Normally, when we do this, what has to happen is we say, I want to access address OX2. The hardware says, when we do that load from OX2 or that store to OX2, the hardware says, okay, I don't actually know where that address is in physical memory. And so it has to do this lookup in the page table to find the page number and translate that to a frame number. So to make that process faster, we can cache the result of that translation. So the first time we go to get this page number 00 and the frame number 01, we can store that in this cache. And we probably have it so that the ASID is like the process ID, essentially. Roughly the same thing. The only difference is that with like an address space identifier, we can share things in the TLB versus if we have the exact PID, then we have sort of the same issue where if we're sharing memory now, we can't have the same cached thing on the TLB. So this TLB has two entries, and we're going to index into it based on the address. So based on the bits of the either physical or virtual, or the virtual address, that's what we're going to store in this TLB. So we have this virtual address that is 0010. The part of that is the page number is the 00 part of it. So what we want to do is take some part of that page number and use it as our index into the cache. So let me actually make another column here. Insert one left. So this is the index on the left here into the cache. So we're just going to have 0 and 1. So we're going to say this is a 2-entry TLB. That reduces the size. It's probably pretty reasonable because we'd have a data cache that is a similar size here. And so we basically want to make sure that the TLB covers the same amount of space as the data cache does. When I say covers, means like the same amount of memory. So whatever memory we can store in the data cache, we want to make sure we have the same stuff stored in the TLB at the same time. So we have two indexes, and we have an ASID, and then we have a page number and frame number. So when we access this, we're going to check first to see, do we have this entry at index 0 in the TLB? So if we have the page number to frame number translation there for this process, we don't have to go to software anymore. We can just quickly, while we're doing this store or load at the hardware level, we can look at that bit of the address and see, oh, hey, we're going to index 0. That does match the page number, so we found that it is exactly the same. The 00 is the same as 00. And so we can just substitute frame number into that address, replace the 0, 0 with a 0, 1, leave the offset the same. And that gives us the actual physical address that we can send to the MMU, like the memory management unit, to request that address. And that means that we can quickly get it if it is in a data cache somewhere or an instruction cache on the system. We have that physical to virtual translation immediately, or virtual to physical translation immediately, rather than having to wait for the software to go and find this in the per process page table. We might have other things in here. You know, we could have ASID 1, and that could show that we have this mapping from 1, 1 to 1, 1 as well. You'll notice here that we can only have one or the other. So because of the fact that this is a cache, and this is smaller than the entire page table, we want to make it smaller so we're not using the same amount of space as the page table, since, of course, if we have like 2 to the 48th possible addresses, that's a lot of pages. That's a really big hardware structure. It's going to be too slow at that point. So we want this structure to be small, and we want to make sure that, you know, it holds enough that we can make memory accesses fast, but not too large that it, you know, sort of outweighs its benefits. So you notice that, like, if we then accessed a page, you know, maybe we did this address, and then we also accessed after that, maybe we did an access to OX7. OX7 is going to be the address 0111. That translation means that we're going to go, sorry, not OX7. It's another one of the maps here. 10, sorry. Let's say we ended up mapping in address OXA, which is going to be 1010. So now, again, we're going to look at the page number. We're going to pull out that 1 bit that is our index into the TLB. So basically, what we're going to do is use the page number as the way to index into the TLB. We're going to use the bottom bits of that as our index. So, you know, we basically cut it in half to find our page number, and then however many bits we need to index into the TLB, however many entries we have is what that's based off of, we're going to use that bit. So we're going to use bit 0. That means we're going to go into this index. We're going to see that this is not the correct page number that we're looking for. So we're going to replace that with 10, and we're going to do the software page table walk and find that that would map to 10 possibly, and that's what we're going to store in this TLB entry. And that'll allow us to do the translation to 1010 equals OXA. So this is like assuming that we were going to map this page into memory and replace the one that's there and do all that sort of stuff as well. But hopefully that clears things up a little bit. Are there any questions on the use of the TLB? Okay, cool. And again, this is just an optimization that makes it a little faster to do this in hardware. So let's do this practice problem then. Let's split up into our groups in Discord and take maybe 2 minutes, 2-3 minutes to do this. So if you can split up into groups, and we want to figure out for a 32-bit system with 1 kilobyte pages. We're accessing the address 1, 2, 3, 4, 5, 6, 7, 8. We want to know what's the page offset, what is the page number for that address, and if we have an 8-entry TLB, what is the index that we are using to get that page number. Okay, let's go ahead and take 3 minutes to work on that. I will try and check on you as you're working. How we doing? Did I see what? So how are we doing with it? Yep. So the 10 bits would be the page offset. So 1 kilobyte pages means that's the size of the page and the size of the frame. So that's the back half of the address. It would be part of 6 and then 7, 8. Yeah, because it's 10 bits, right? So the back part of 6 and then 7, 8. Yeah. Yeah. Emily, it sounds like you were on like digital audio or something. Is anyone else hearing her normally? I'm hearing like. Yeah, because it's definitely, it sounds like I don't know, some really fast typing or something. Maybe. Yeah, so the page offset, yeah, that's great. So the page offset is the back half, and then the page number is the first part. So then for the index to find the TLB, how many bits do we need to represent 8 entries? Yep. So those would be the last 3 that we have in the page number. Yep. Cool. Okay, you're good. Move on. How are we doing middle row? Mm-hmm. Okay. Yeah. Cool. Okay. Yeah, and then for the TLB, how many indexes do you have for 8 entries? So 2 to the what equals 8? 3, yeah. So you're gonna have 3 entries. So that should be the last 3 bits of the page number are what we're gonna use as our index into the TLB. Yep. And I'm gonna check on front row real quick. Hi, front row, how are we doing? Good? What do we get? Right. Okay. Um, mhm. Yep. That's correct. Yeah. So because we have those 8 entries, it's 3 bits to represent those. And so we would use like the last 3 bits of the page number basically as our TLB. Okay. Shifting the page. Right. Yeah. Yeah. Right. yeah, so we would need to shift things a little bit in order to make that work. But yeah. Okay. Cool. Let's go back to the Hangout then. I don't know if you have to stay in this or not. If you're still getting audio from Google, that's great. Otherwise, shift back into the lecture channel. Okay, so I think most of you got it. So 32 bits, 1 kilobyte pages. Because we have 1 kilobyte pages, that's 1,024 bytes, which means we need to represent, we need 10 bits to represent that. So the last 10 bits of OX1234, so OX12345678 is going to be all of these bits here, 0111, 1000. So those are the 32 bits for this address spelled out. So our page offset should be the last 10 bits of that. So we're just gonna basically figure out what those last 10 bits are, and that should be the last 2 bits of 6 and the final bits in that system. So 100111, 1000. Yeah. So that's our page offset. We're just taking the last 10 bits here. The page number, delete this column for now. So the page number is going to be the remaining bits that we had left. So everything that was not part of the page offset is the page number. And then the TLB bits, so our page offset is 10 bits. Bytes equals 1 kilobyte. Page number is 32 bits minus 10 bits equals 22 bits. And then our TLB, if we have 8 entries in our TLB, that means we're going to have 8 entries implies 3 bits because 2 to the third is going to be 8. So we have 3 bits to represent 8 different values for our indexes. And that means that we're going to find that index at the last 3 bits of the page number. This would be index 5 in our TLB here. So we're just looking at that last couple bits here for our TLB entry. Okay. Any other questions on this setup here? Okay, cool. So let's just talk then briefly about some of this other stuff that I have here. And we'll finish up with this. So there will be no reading quiz for Monday because you've already done the reading quiz on the page table structures. I just wanted to make sure we took a step back and everyone really understood this before we moved on. Yeah. Yeah, this is the hardware structure that would allow us to translate quickly. So it has the index is where we find the data. We check to see that the ASID is the same as the one we're looking for. So making sure that like this is the right process stored in the cache. And then we have the translation already. So we don't have to go to the software page table, which is usually going to be a lot larger. Like normally we're having to search through like, megabytes worth of data to find the correct page to frame number mapping. Yeah, so yeah, instead of just 1 bit, yeah. Cool. So we talked about sharing a little bit already, and we should also talk about page protection. So normally this page table would have a little bit more stuff in it. It might have, if we have, permissions, and that permissions might be like 3 bits probably, and those bits are usually then going to be like permissions for read, write, execute, something like that, or execute, write, read, I think is what they actually mean on a Linux system. So if it's like 111, that means you can do all of them. If it's 000, that means you can do none of them. Usually we have the configuration that it's executable and readable or readable and writable. so that we can, make sure that the system security is maintained. We generally don't want people to be able to write to code or to be able to execute data. That's generally a bad security decision. That's how most buffer overflow attacks will happen, or like older buffer overflow attacks. So if we maintain these sort of mappings where we have read and execute or write and read, but not write and execute at the same time, that means that we can be pretty secure. So pages will have these permissions attached to pages. If you try to do something wrong to a page or try to access a page that you haven't mapped already that's invalid, that's when you get a seg fault. So if you see segmentation fault, that's what has happened. It's probably due to the fact that you ran over memory or used memory that's been deleted, but it's going to result as a segmentation fault. We can share pages among multiple processes, and this can allow us to do things like share common code like libraries and share data between processes. So we can manage these things with mmap. So this is the man page for mmap. And you can see, I think I used this before in class, but we didn't really talk about it. So when you mmap a page, you give an address that you would like to request. If it's able to give you that address, it will give you that address. If that address is already mapped to something else, it'll tell you no and throw an error back at you. Usually you call this with the address being 0, so you're just saying, I would like some memory that has these properties. You tell it the size of memory that you want. You give the protection level. So protection is what we just talked about, which is protect exec, protect read, protect write, or protect none. And it's kind of a weird nomenclature because it's protect write means that you can write, protect reads that you can read, etc. Flags are some things to say whether we want it to be shared, whether we want it to be private, and then there are a number of other things like you can say that you want it to be anonymous, so it's not backed by a file, if you want it to be backed by a file, and then you can do the sort of huge page mapping that we talked about a little bit, where if we want larger than the standard page size, we can ask for a 2 megabyte or even a 1 gigabyte page in memory. So we'll pick up with this and talk about the final question there. If you want to think about security implications of processes sharing code over the weekend, that'd be great. Otherwise, I know you have some homework and stuff to work on. So if there are no more questions, I will see you on Monday. Have a good weekend.